In continuing on and talking about 11.2, we now want to talk a little bit more about one-sided limits and actually start the process of discussing difference quotients. So we previously talked about one-sided limits in 11.1 because we defined a limit as the existence of a limit, I should say, as the value that f of x approaches as we approach x from both sides. So if you look back to this notation for a one-sided limit, we said the limit of f of x as x approaches c from the left side. So again, this little notation up there just simply means we're approaching c from the left. The limit of f of x as x approaches c from the right, which just means we're just approaching from the positive direction. So we have one-sided limits, and we use them to discuss the existence of a limit. Specifically, if f of x is a function and c is some real number as well as L, then we can say that the limit of this function is that value L if and only if we have the same limit as we approach from the left as we do from the right. If we don't agree upon the same number, then the limit there does not exist. And we discussed this back in 11.1 as one of the scenarios in which a limit would not exist. But let's go a little bit further into that and try a few practice problems with this. So we've got another piecewise function here. So let's go ahead and start by actually graphing this piecewise function before we actually find any limits. So starting with this, let's go ahead and look at when our x value is less than -3, then we have negative x. Remember what that means. It doesn't mean that I just go ahead and just start graphing negative x from that point. What we're saying is we're going to graph negative x, but we're really only graphing it from the point -3. So if our y-intercept is at 0 and our slope is -1, then what we have here is a graph that should look something like this. Now, had I continued this line past -3, it would go through the origin and continue on down with a slope of -1. But this function only exists when x is less than -3, not less than or equal to. So I'm going to draw this little hole here just to indicate that it's not defined at -3 for that piece. Now, when x is greater than or equal to -3, then I've got the function -1/3 x. So let me actually just do that in a different color, just so we see what's going on there. So for -1/3 x. So for that, I have, again, a y-intercept of 0, but from there I've got a slope of -1/3. So that's up 1, back 3, which is a point there. Or from there, I can say let's see. Oh, sorry, down 1 over 3. Sorry, I had just a little bit of a brain fart there. Let me clean that up. All right, so I'm going to go ahead and graph this line going that way. Okay, and thank you, iPad, for cleaning that up and just make sure it's continuous. All right, so now that we have that graph there, let's look at a couple of limits. I'm going to zoom out just so we can see the limit statements. So what is the limit of this function as x approaches -3 from the left? So as we approach -3 from the left, in other words, we're going in this direction, what is our function approaching? Our function appears to be approaching this value, which would be what? It would be 3. So we can just say 3, but if I want to just do this algebraically, I could say, let's try the direct substitution. We're going to plug in -3 into our function. Well, which piece would we plug it into? Since we're approaching from the left side, we want to plug it into this piece. So we're saying -3. Well, that's just +3. And that's confirmed for us by what we're seeing here in our graph on this point. All right, let's try another one. Let's try approaching -3 this time from the positive direction. So what's going on as we approach -3 from the positive direction? Well, again, let's think about which piece we're looking at here. Are we looking at which of these two pieces up here? We would be looking at the red part of the graph, if you will, right? Because we're approaching from the positive direction, it makes sense to be looking at the red graph. So we're going to then evaluate negative 1/3 at negative 3, and that just gives me positive 1. And let's check to see that's confirmed in our graph here. And indeed, as we approach negative 3 from the right side, looks like our red graph is getting closer and closer to the value of 1. So to finish this off, answer. What is the limit of this function as x approaches negative 3? And the answer is, it doesn't exist. It doesn't exist, and we can write dne because, and let's write our justification for this, the limit as x approaches negative 3 from the negative is not equal to the limit as x approaches negative 3 from the positive. Because those two aren't agreeing. This black side here is saying I'm getting closer to positive 3, and the red graph, that piece, is saying I'm getting closer to 1. They are not agreeing on the same value, therefore the limit of this function does not exist as x approaches negative 3. Okay? All right, so now without relying on the graphs, let's try to do some one-sided limits and see what happens here and see if the limit might exist. So for this first problem, what is the limit of this as x approaches 1 from the negative? Well, one thing that you could just do here is just ask yourself, okay, try the direct substitution. If I'm approaching 1 from the negative, well, I'm going to get 1/0, which is undefined. But since we're looking at a one-sided limit, instead of thinking about it this way, let's just ask ourselves, if I'm approaching 1 from the negative direction, can I try plugging in a number that's really, really close to 1, but to the left of it? So what would be a number that would be very close to 1, but to the left? We could try something like 0.9 repeating all over 0.9 repeating minus 1. Well, what's going on in that denominator down there? Well, if it's 0.9 repeating minus 1, then you're getting some negative value. We're not sure exactly what this is. It's going to be some very small value, but we know it's going to be negative. It's going to be less than 0. And we can't take the square root of a negative number. So it's undefined there, right? So this limit here, we can also say doesn't exist. It's undefined here, right? Okay, so let's go ahead and try another one. What about as we approach, and there's a little bit of typo here. I don't need these plus signs, unnecessary. So that's a little bit of a typo, sorry about that. All right, so let's just look at the same function now. What happens as we approach 1 from the right side? So just like we did before, let's try choosing a number that's really close to 1, but to the right of it. So something like 1.1, for example, over 1.1 minus 1. Well, this time our numerator is indeed a positive value. So we can take the square root of it, but think about what's going to happen as we take the square root of something like, well, let's just write this, 1.1 over the square root of 0.1. And it's going to give us a smaller number. And we were fortunate because we worked with 1.1, but what if I had chosen 1.01 or 1.0000001 and taken the square root of that? What's going to happen to our denominator? It's going to get very small in value. In other words, this is going to get closer and closer to infinity, okay? Now, remember what infinity means in terms of a limit. Infinity cannot be a limit for a function, but in calculus, it's often used to describe a one-sided limit because it actually gives us a little bit more information. So it is not inaccurate to say that this limit is equal to infinity. You're allowed to say that when you're describing a one-sided limit. So okay with one-sided limits. Just remember again, infinity cannot be a limit. It's not something you ever reach. But it's okay to describe a one-sided limit using infinity because it just gives you a little bit more information there instead of just saying does not exist. It's, yes, the limit doesn't exist, but we can say it's equal to infinity. All right, let's try 2 more problems now. This time we're approaching -3 from the right side. So since it's -3 on a number line, just think about this for a second. Since we're approaching -3 from the right side, we want to choose a number right before -3. So something like -2.99. So let's see what that's equal to. -2.99 plus 3 over -2.99 plus 3. And that would give me the absolute value of 0.01 all over 0.01. And that's just going to be equal to 1. So that limit does exist. What about for the same function as we approach -3, this time from the negative? So we want to choose a value that's a little less than -3. So this time we're going to go the absolute value of -3.01, for example. And you can use any number that you want. It's a little arbitrary, as long as it gives you a good picture of what's going on here with the limit. And to clean that up, that gives me -0.01, the absolute value of that, over -0.01. Well, the absolute value in the numerator is going to make that positive. So we've got positive 0.01 over -0.01. And that gives me just -1. So then if I were to ask you, what is the limit of this function that we've just worked with as x approaches -3, we would say that limit doesn't exist. Because from the positive, we're approaching 1, and from the negative, we're approaching -1.